So there's just one important piece we have yet to cover, and that's the user interface for the interpreter. How should it behave? So interpreters typically have what's called a read-eval-print loop. So the user interface for a programming language is this interactive loop where you enter an expression and then it gets evaluated. So here's the process of a read-eval-print loop. Print a prompt telling the user that the computer is ready for its input. Read text input from the user. Parse that text into an expression or statement. Evaluate that expression. If any errors occur, report those errors. Otherwise, print the value of the expression and repeat, printing another prompt. So that read-eval-print loop is a way that a person can interact with a programming language by typing expressions into its interpreter and seeing the values. And that's exactly what we're doing here. So as you can see, we type in an expression, it gets evaluated. What code is actually doing that? Well, we have a read-eval-print loop, which forever tries to read in some text from the user. And while there's more text remaining, it parses the expression using the scheme read function, which gives us back an expression represented as a scheme list, and then calls calc-eval on that expression in order to evaluate it and prints the result. Now notice that print will only happen if there aren't any exceptions raised during calc-eval, because if there are exceptions, then this won't actually have a value. Now, throughout the program, we raise exceptions. Exceptions are raised within all aspects of an interpreter: lexical analysis, syntactic analysis, eval, and apply. So for example, when we reach the token 2.3.4, which is not a well-formed number, we might get a value error. Syntactic analysis is in charge of making sure that structurally our expressions are correct. So having an extra close parenthesis will raise an syntax error saying unexpected token. Eval makes sure that we're only dealing with two types of expressions: primitive and call expressions. And so, for instance, it can detect things like noticing that there's an empty combination, which is not a number or a call expression. And then apply actually does quite a bit of error checking, because it actually knows which operator is being applied and what are the rules for those operators. So it can find that if there are no arguments to minus, we should raise a type error that says minus requires at least one argument. So in the version of calculator that we've built, all of these things apply. We get a value error, we get a syntax error, we can get a type error, and we can get a type error that tells me specifically for this operator that I've chosen, I need at least one argument. And if you look in the source code, these are raised all over the place. So here's a raising of the type error, here's another type error, but some of these are even in different files. And some of them will actually be raised by Python itself. So what happens if I divide 1 by 0? Then I'll get a 0 division error, which is something that happens when you use the built-in division function that we're using to implement divide. So divide is carried out by the built-in division, or the built-in true-div operator, and both of those are able to raise 0 division errors when they run into trouble. Now, handling exceptions happens all in one place, in contrast to raising exceptions, which happens all over the place. So an interactive interpreter should print information about each error, so that when those errors occur, the programmer who's generated them can figure out what to change in order to get rid of the error. And a well-designed interactive interpreter should never really halt. It should stop evaluating the current expression and print out the error, but then give the programmer a chance to revise what they've done. So the user should have the opportunity to try again in the current environment, instead of having the whole program crash. And that's exactly what happens here. So as you can see, I'm able to continue entering expressions. The only way I can quit out of the scheme calculator is by pressing, in my system, Control D, which says this is the end of the file. And then it will say calculation is complete. And finally, the program will end. Now, how do we control for all this? Well, we put both the parsing and evaluation within a try statement that knows to look for syntax, type, value, and zero division errors, all the things that can occur, and just prints those errors out. And then, since this is all embedded within the suite of a while statement, we'll go back and try again. So the only way to stop is to reach the end of a file, or a keyboard interrupt, at which point it will print calculation is complete.